to the cloud. All right. Hello, everyone. Today is the lecture number 5, and let us again start with the brief recap of what we've done last week. So basically, last time we've started from this statement that any the sum of outer products of the vectors give us the unitary vector or unitary operator or identity operator, right? If these vectors belong to the basis. Okay, and then we have started the discussion of basics of quantum mechanics. Okay, so we decided to go through this introduction to quantum mechanics in the form of the series of postulates, and the first postulate is the postulate of the representation of a state of a quantum system in form of a vector in the complex Hilbert space, right? We say that in order to describe a state of a quantum system, we introduce this psi vector, psi state, and in order to represent this vector, we can introduce the basis of unitary vectors, and this basis can be finite or infinite dimension, and hence this vector, this psi vector, is given by the projections of this psi vector on the corresponding basis vectors. Okay, and the total psi vector is given by the superposition of these basis vectors with corresponding components Cn, which are the essentially projections on the basis vectors. Then we discuss this example. Let me mute this. All right. Yeah, for example, if you have a particle like an electron, which is known as the classical quantum example, right? The quantum system, example of a quantum system, and let the particle pass through a slit in a screen, then this particle can take any direction after the slit, basically. And if we enumerate these directions or paths 0, 1, 2, etc., the total psi state after the slit is given by the superposition of all these possible states. And before we do the measurement of the particle in a particular state, we have to take into account all these states at the same time. So experiment tells us that the particle not actually goes one of the states. It it goes in all of these states in the same time. This is maybe the most curious part about quantum mechanics and quantum physics, that multiple realizations can exist in the same time, right? And before we do the classical measurement, we have to take into account all of them. And we also call this as quantum parallelism. Okay. Another example of two states, or like two-level system, or a qubit, right? So this is the simplest possible quantum system, which gets only two states. And again, we have to take into account the existence of all these two states in the simultaneously in the same time. The postulate number 2 tells us that it actually brings the physical meaning to the coefficients C1, C0, C1, Cn. So these coefficients, they give us the probability amplitudes of finding a system in a particular state. Okay, and this is probability amplitudes, and in order to get the actual probability, I have to take the absolute value squared. So the absolute value squared of each coefficient gives us the probability of finding a system in a particular state. For example, going back to this example 1 of a particle passing through the slit, this Cn gives us the probability of going along the path n, right? C sub 0 gives us the probability of going to the path 0, etc. And of course, since the total probability is 1, these probabilities must be normalized so that the sum of all these probabilities gives us 1. So then postulate number 3, physical observables are represented by Hermitian operators. Okay, why Hermitian? Because Hermitian operators have real valued eigenvalues. Okay, and since physical observables, they are real numbers, so the Hermitian operators are the right operators to represent physical observables, right? So in quantum mechanics, all the classical quantities that can be measured, they are promoted to Hermitian operators. Okay, promoted to Hermitian operators. For example, we discussed this Hamiltonian of a general qubit. So we state that a qubit can get an energy, right? And the corresponding operator of energy is Hamiltonian. Okay, and so we introduced this operator, Hamiltonian, and the main part about maybe investigating in quantum system is to construct the Hamiltonian based on some approaches. Okay, for example, we constructed this Hamiltonian of a qubit. Then we can solve this eigenstate eigenvalue problem, this EEE problem. And solving this problem, we can find the eigenstates and the eigenvalues, and the eigenvalues of the Hamiltonian are the energy states, energy levels. Today, later, we will discuss another very classical problem or textbook problem for solving such an equation. Okay, so solving this problem, we can find the energy levels, for example, 0 and 1, and corresponding solution for the qubit will be probability amplitude 0 times the eigen state 0 plus probability amplitude 1, C1, times the corresponding eigenstate 1. Okay, and in the energy representation, we said that in energy representation, this Hamiltonian will be given by a matrix 2 by 2 with the eigenvalues on the main diagonal E0, E1. Pretty straightforward. Yeah, another point is that the free particle is given by the Breuil wave function, which is essentially the plane wave in a free space. Okay, and at this point, there is this famous Einstein's formula for the momentum of a free particle, which is simply the wave number k times Planck's constant. Okay, so Einstein introduced this formula to describe some experiments by that time when people were not like convinced about quantum mechanics and etc. So he introduced this formula for the momentum, and there was a formula for the energy. So formula for the energy, which is known as Planck's formula, right? Yeah, and then we discussed the coordinate representation. So in the coordinate representation, the operator of coordinate is given by the coordinate itself, and momentum operator is given by this construction of minus I h bar nabla operator. Nabla operator is this composition of the partial derivatives by x, by y, and by z multiplied by corresponding unit vector I, j, and k. Okay, so it's supposed to be pretty known from other courses from calculus. By components, right? These three formulas represent the components of the momentum operator x, y, and z. Okay, so and the last one we discussed, last postulate we discussed last week was about projective measurements. So it is essentially about the concept of measurement in quantum mechanics. So whenever we do measurement of a quantum system, we put this quantum system in an interaction with a classical object, right? So we have some classical object. We call this an measuring apparatus, equipment, and we put it in contact with quantum system, and this quantum system changes the state of a classical system, of the measuring system. And this is how we observe this action from quantum to classical. Okay, and when this happens, the quantum system changes abruptly and spontaneously. It changes the state from the superposition of states to one particular state of the system. It is represented by this line here. So suppose we have a psi vector, psi state. So there is a question in the chat. Is there a way to use quantum sensing to not disturb the state of the quantum system? So the answer is no. We cannot measure quantum system without acting on it. But there are other types of measurements that reduce this action on the quantum system by some amount, by some level, but the action is always there, so you cannot measure without acting on it. Probably we will discuss this another type of measurements in what follows. because they are also important for quantum computing. But this is just the introduction, and this is the classical type of measurement, this projective measurements. Okay, so the quantum system collapses to one of the possible states. Okay, and we cannot predict which state it will be. What we can say on only the probability of finding the state in the particular final state, in the resulting state. Okay, so mathematically this projective measurement can be given by an operator. It's called projective operator. Is just given by the outer product of the corresponding states, psi m times psi m. So this projective operator will project any psi vector, any state on the psi vector m. Okay, so this is where we ended last time. Let me drink some coffee. Okay. So about these projective operators, let us, for example, consider one property of this projective operator. The first property is the fact that when I take the projective operator twice, the result is just the, as the projective operator itself. Or if I take it 3 times or 4 times, the result is always the same. So, for example, if I have a state psi, right, and I apply my projective operator on this state psi, it is essentially applying this operator, this outer product of psi m, and then vector psi. Okay, and this is nothing but psi m, then psi m, and psi state. Okay, so this is just projection of psi on a psi n, which gives us coefficient cm, right? So the result will be some constant cm and the vector psi m. So this is how this projective operator works. And in order to prove this statement, I simply write this projective operator psi m, okay, and take it twice. So it's going to be the psi m, another psi m, okay. So because this psi m is the state with the amplitude 1, so this inner product here gives me 1, okay, and the result is psi m cross psi m. So, and this is equal to the projective operator Pm. Okay, so And likewise, if I take 3 times, 4 times this projective operator, the result is just projective operator itself. Okay, so let us consider an example. So for a state phi, let's call it phi. Let's make it normalized, so it's supposed to be square root of 5 to 1, right? So 2 to the power of 2 is 4, 1 gives 5, so 1 over square root of 5, so this state is is normalized. We need to construct the operator that projects on the state phi. So this is the goal. So any projector is given by phi cross phi, right? Which gives us for this particular vector for the cat, I have 1 over square root of 5, then column 2, 1, and then for the bra, I take it transpose and complex conjugated. So it's going to be 2, 1. Okay. So the product 1 over square root of 5, 1 square root of 5 gives us 1 over 5. And then we have this 2, 1, 2, 1. Okay. And the result is the matrix 2 by 2, which is 4, 2, 2, 1. Okay, so this matrix is a operator that projects any state on the state phi. Okay. Pretty good. So it was postulate number 4. Do you have any questions about this part? Okay. So it was postulate number 4. Let's go to postulate number 5. Postulate number 5. So the postulate number 5, let's formulate this this way. So when you measure quantum system, as we just discussed, with this projective measurements, the system collapses to one of the possible states, and the only thing you can predict is the probability of the final state, but not the exact, not exactly the one, right? And and if you measure some physical quantity, for example, the energy or coordinate of a particle or momentum of a particle, you will get different values, different result, but only those from allowed results, only the eigenvalues of the corresponding operator. Okay, and if you do this measurement many times and you average the result, you will get the average result of the measurement, and we will call this result as an expectation value. So the expectation value is the value that is most expected from the experiment. Okay, and this postulate number 5 says that the expectation value of some observable for a quantum system in a particular state psi is given by the matrix element in the corresponding state. So let me write it this way. So the expectation value, the expectation value of measurement the system, of measurement the observable let's denote it by O operator. So it's an operator that corresponds to some observable energy, coordinate, momentum, etc. So it's observable O for a system in state psi is given by this construction, this matrix element. So we denote the average by this sign, these brackets, right? So this is the average or expectation value. It's gonna be psi, then operator O, then psi. Okay, so the result of this operation will be the number, and that number represents the expectation value of the corresponding observable. Expectation value of a corresponding observable. So let us consider a couple of maybe problems to exemplify this. So let's consider problem number 1. And let's take Hermitian operator of some, the simplest Hermitian operator, like 2, 1 minus I here, 1 plus I here, 3, right? So again, I remind you that Hermitian operator, the operator that doesn't change after Hermitian conjugation. The Hermitian conjugation is transposition and complex conjugation. Okay, so this operator is Hermitian. Okay, and let me take some state psi, like something like this, I and 1, and and now I'm asking what will be the so if I have a system that is that has a observable, for example, energy with this operator H, and I prepare my system in this state psi. So what will be the observable for this quantity? Okay, and to do so, I basically apply this formula above. So I write the expectation value for this quantity H, okay, and it's equal to this psi H psi, okay. So first is the bra I transpose cat and take the complex conjugation, right? So it's gonna be minus I1, then the matrix, the operator of H, 2, 1 minus I1 plus I3, second, and the third is the cat I1. Okay. Okay, I just take the matrix product of these two, and then the second one. So for now, I get minus I1. This is the bra vector. Then second one will be 2 times I, gives me 2I, plus 1 minus I times 1, which is 1 minus I, right? And the second, it's gonna be I times 1 plus I, right? And plus 3 times 1, which is 3. Okay. So it's gonna be minus I1. And the second one is 2I minus I is I plus 1. And the second is I plus I squared, which is minus 1 plus 3. So it's I plus 2. I plus 2. Okay, and finally, the product of these two vectors is minus I times I plus 1, right? Yes. And plus I plus 2. It is equal to minus I times I gives us plus. Yes?
I am so sorry. Could you scroll back up just a little bit while you write so I can continue to take notes?
Sorry.
No, it's
Is it
okay.
better?
Thank you so much. Yeah, that's perfect. Thank you so much.
Okay. All right. So the minus I times I gives us 1. All right. Then minus I, then plus I, and finally plus 2. Okay, so minus I plus I gives us cancel out. So the answer is 3. Okay, so the expectation value is real valued, and in this case it is equal to 3. So there is a theorem that the expectation values of Hermitian operators are real valued. Okay, so just like in this case, for this simplest Hermitian operator, the expectation value is real valued. Okay, so this is the way how for any operator of any observable in a particular state, we can get the expectation value. But what we don't know the state, right? So in this particular case, on this problem 1, we assume that our system is in this is prepared in this quantum state, psi I1. But what if we don't know in which state it is prepared? In this case, we will get the matrix of expectation values. So let me consider this problem number 2. Problem number 2. And let's take this simple operator sigma x. We will discuss today what it corresponds to, but for now I mean, for now it's just a matrix 0, 1, 1, 0. Very simple one. Again, this is Hermitian because you transpose and complex conjugate is the same. So it is Hermitian, but trivially Hermitian. And let's consider a two-level system like a qubit, and this qubit can exist in only two possible states. So the first possible state is given by this state, 1 over square root of 2, and the column vector 1i, and the second state is the same, but the minus I here. Okay, so the problem is to find the expectation value for this operator sigma x. Okay, so in this case we have two states, and all expectation values can be written as a matrix of the following form. So I can take first state and first state. So it's gonna be first state sigma s first state. Okay, I can take first state and second state. So it's a first state and the second state. I can take second state and first state. Second, first, and finally second and second. Okay, so it's a matrix like this, 2 by 2 matrix composed of the all possible expectation values for these two states. Okay, so let's go and calculate these expectation values first for the first state. So for the phi1, I have 1 over square root of 2 twice, so it's going to be 1 over 2, right? Then bra f1 is 1 minus I, because complex conjugation and transpose. Then the sigma x is 0, 1, 1, 0, and the vector ket 1 I. Okay, a row by column, we take the product. It's gonna be 0 times 1 plus 1 times I, which is I, and 1 times 1 is 1, so it's gonna be I and 1 equal 1 times I is I, plus minus I times 1 is minus I. Okay, so I minus I is equal to 0. So the expectation value for this state is 0. Pretty good. And of course the expectation value for the second state is also 0, because the difference is just minus here, right? So the expectation value for the second state is also 0. And when this situation appears, it simply means that this observable cannot be measured in this particular state. Okay, so the result is 0. So you measure nothing. In this particular case, sigma x, it doesn't correspond to any observable. This is just a matrix for an example of how all this machinery works. Okay, and what is left? The only cross elements like phi1 sigma s phi2, right? So it is equal to 1 over 2 1 minus I for the phi1 bra, then 0 1 1 0, and for the cats we have phi2, which is 1 minus I. Okay, so the result of a product of matrix time vector is 0 times 1 plus 1 times minus I, so it's minus I here, 1 times 1, 1, okay, and finally this gives us the inner product of two vectors, 1 times minus I minus Y, plus minus I times 1, which is minus I. Okay, so the result is minus I. Minus I. And the second cross observable phi2 sigma s phi1 is going to be complex conjugated version of this, but let's confirm that. So it's going to be 1 over 2 1 I for the bra phi2, then 0 1 1 0, and 1 I here. Okay, 1 over 2 1 I. Okay, the product of matrix and the vector 1 times I is equal to I. 1 times 1 is equal to 1. Excuse me, 1 over 2 I plus I, which is equal to I. Okay. So this, a few words about the matrices like this. So as we say, this diagonal components give us the probability of finding the system of, of probability of, it's not probability, it's expectation value of observing the physical quantity in the corresponding state. For example, this one 1 1 would give us the expectation value in the state phi1. The second element is the expectation value in the state phi2. But these off-diagonal elements, they have a little different meaning. They correspond, they give us the expectation value of transition from one state to another state. Okay, for example, this phi1 sigma x phi2 corresponds to the transition from phi1 state to state phi2. Okay, so they play a little bit different role, but the machinery is here. This is how we calculate these matrix elements of an operator in the given states. Okay, so it was postulate number 5. So let's go ahead to the postulate number 6. Postulate Number 6. So you, of course, know that in quantum, the different quantities can be not simultaneously measurable. Like this notorious example is the coordinate and momentum, right? Like the x coordinate cannot be simultaneously measured with the x component of the momentum. And that's simply because the quantum system is so fragile or so small, and when you measure the coordinate, you of course you alter the system so strongly, so the second quantity, the momentum is not measurable anymore. If we return back to this picture here, this example 1, right? So when the particle passes through the slit, we know, of course, this coordinate of the slit, and we can tell approximately the position of the particle, because it's defined by the position of the slit. But when we do so, we change the system. We change the state of the system, and after the slit, it turns into the superposition of all possible paths, path 0, 1, 2, etc. And of course, all these paths, they have different projection of the momentum, right? And hence measuring coordinate affects the state of momentum. And likewise, measuring the state of momentum changes the coordinate. Okay, so this postulate states that in quantum, not all quantities are measurable simultaneously at the same time. So let us express this way. In quantum, any two quantities can be measured in one experiment, or simultaneously. If their operators commute. So this new word, commute, commutation. So when we are talking about commutation, we consider two operators or two matrices, A and B. And if these operators commute, it means that the product of these two operators don't depend on the order. So the A times B is equal to B times A. Okay, and so when this is true, when the operators commute, meaning the order, it doesn't matter in which order you take the product, then the two quantities can be measured at the same time, simultaneously in one experiment. If not, so this is commute. The operators commute. If AB doesn't equal to BA, they don't commute. don't commute. And in order to check commutation of any two operators, people introduce this commutator. So the commutator is it's written this way: a comma b. Okay, so by definition it is a times b minus b times a. Okay, so this is commutator, expression for the commutator. Commutator. So in terms of commutation, we can have two types of operators: commutative operators and non-commutative operators, right? So for example, for the commutative operators, for the commutative operators, the commutator is equal to 0. Is equal to 0, which means AB equals to BA. Okay, and one example of this would be like two coordinates, right? So in the coordinate representation, as we already discussed, the coordinate represents the operator of the coordinate is the coordinate itself. For example, if I take the operator of a coordinate x, which is x, and multiplied by the operator of coordinate y, which is y, I mean, of course, the result of this doesn't depend on the order of these two. This is the simple example. Another simple example is the fact that the identity operator commutes with any operator. So when I take this identity operator on the left from the operator A, is the same as if I take this operator on the right. This I is identity operator. And of course, there are other types of commutative operators. For example, px operator and y, right? I remind you that px operator is minus I h bar d over dx. And of course, this d over dx partial derivative doesn't act on y. So when I write this minus I h bar d over dx, y here, of course I can exchange this partial derivative by x and y, because partial derivative by x doesn't act on y. And for this reason, we can measure the coordinate y and the momentum x in one experiment. So these two, they commute, and they can be measured in one experiment. But however, this for example, this px and x, they obviously don't commute, because px is minus ih d over dx, and this d over dx acts on x, right? It's not now it matters in which order you write the operators, which means that px and x cannot be measured in the same experiment with high accuracy. So this is for So this is for the commutative operators. And the second one is non-commutative. Non-commutative. Non-commutative operators. So as we just discussed, the x and px, they not commutative. So the commutator in equal to in 0. In equal to 0. Maybe let's express this. I mean, let's discuss this here and again. So this commutator x px is x times px minus px times x. Okay. And this commutator is, of course, operator, right? So this px, these are operators. And of course, this operator acts on some function. On some function. Let me. So some function psi. Okay, so I write this psi here and psi here. So this operator acts on the function. Okay, and the function, of course, is a function of x. It can be a function of x. Okay, so if I expand this parenthesis, I get. Well, actually, let's write one term by one. So for the first one, x px psi, depending on x, I get x, then minus I h bar d over dx, right? This is the operator px. Okay, and the psi function x. Okay, so it's equal to minus I h bar x d psi over dx. Okay, and this is first term. Second term is px x psi x, which is minus I h d over dx, but from x times psi. Okay, so it's gonna be minus I h, applying chain rule, right? So it's gonna be x d psi over dx minus I h psi dx over dx. Dx over dx is 1, so I get minus I h x d psi over dx minus I h psi. Okay, and obviously this one is equal to this one, and the difference is in this last term. So we can calculate the commutator x px, taking the difference of the first term minus second term, and we get I h psi, but now I don't write this psi for the operators, right? Or I can write this in another color like this. So this is kind of important. We will discuss in more detail this fact next week or next time, but for now, just saying that this coincides with the experiment, right? The fact that the coordinate x and the momentum px, they are not that they cannot be measured at the same time with precise accuracy, is expressed in the fact that the corresponding operators don't commute. The commutator is equal to I h bar. Okay. Yes, and so this is the illustration of so-called Heisenberg uncertainty principle. Okay, so let's write this down this way. So in quantum, non-commutative operators have a particular non-commutative operators in quantum have particular importance as they indicate pairs of observables that cannot be precisely measured simultaneously. Okay, so this is the essence of Heisenberg's uncertainty principle. So in quantum, non-commutative operators have particular importance as they indicate pairs of observables that cannot be precisely measured simultaneously. And this is known as Heisenberg's uncertainty principle. Principle. Okay. All right. So if commutator is 0, if the operators commute, the corresponding observables, quantities, can be measured in one experiment. If the commutator ain't 0, if the operators don't commute, then the quantities cannot be measured precisely in the same experiment. Okay, before let us resume and consider one problem from in the matrix form. Okay, so problem about the commutation of operators in matrix form. So suppose I have two operators, A with that corresponds, that's given by matrix 0, 1, 1, 0. Okay, and another matrix, another operator B, 0 minus I 0. Simple two operators, and let's check if A and B commute. Okay, so in order to check if two operators commute, we need to check if the commutator which is AB minus BA, we need to check its value. If it's 0, then two operators commute. If not, they don't commute. Okay, so to do so, let's take the product of matrices A and B. Apparently, the result will be another matrix, 2 by 2. So it's 0, 1, 1, 0, 0 minus I, 0. Okay. Okay, again, row by column. For the first element, we get 0, 0 plus 1I gives us I. For the second, it's gonna be 0 minus I plus 1 times 0, it is 0. For the third, 1, 0, 0 minus I, so it's 0. And finally, 1 times minus I, it is minus I, 0 times 0. Okay. This is the first result of product A times B. So for now, let's take B times A. It's gonna be 0 minus I, 0. And the second is 0, 1, 1, 0. Okay. So here the result row by column is minus I here. Okay. Then 0, 1 minus I 0 is 0. I times 0 plus 0 times 1 it is 0. And finally I times 1 is I. Okay. And so we see that the result is different. So A times B doesn't equal to B times A. So A and B don't commute. Don't commute. So the operators not commutative. And we can calculate the commutator of these two operators, right? So the first result was I 0, 0 minus I minus I 0, 0 I. Okay, so it's gonna be 2I 0, 0 minus 2I, or 2I times matrix 1, 0, 0 minus 1. Okay, so pretty good. So this was the postulate number 6, and let's transit to the second, or to the next one, postulate number 7. Number 7. Let's call this spin. So the existence of the spin and the main properties of spin. So spin, its eigenstates and eigenvalues. Eigenstates and eigenvalues for spin. Right. Here's properties. Okay, so what is spin? Spin is a intrinsic angular momentum of a quantum system, right? And this quantity doesn't have any classical counterpart. It can be imagined as a rotation of a particle around its axis, but in fact it is not the case. It is something that that doesn't have a classical counterpart. So let's write this way. So spin is a quantum intrinsic angular momentum that has no classical counterpart. Classical counterpart. What it means? It means that so if we imagine, or if we describe a quantum system like electron as a particle, in fact, in reality, it's not a particle, right? It is a system that manifests itself as a particle in one experiments and wave as in other experiments. So the behavior of electron really depends on in what experiment, in what situation we observe the electron. And if we observe, I mean, if we consider an electron as a particle, right, we can say that this particle can rotate, it can spin around one axis like this, right? So for example, it can spin in clockwise or counterclockwise direction, and of course it can spin around this axis in the clockwise direction like this, and if it spins, and let's also denote this direction z, for example. So I direct this axis z along the axis of the of rotation, of spinning the electron, the particle. So when it rotates counterclockwise, I denote this by spin, vertical spin s. Okay, so this s stands for spin, and this arrow points the direction of this rotation. And likewise for the spin down, so spin up, spin down. So for the spin down, it is the the clockwise direction of rotation of the spin. So we've got a question in the chat. Is the electron actually spinning? No. So that's what I was trying to say. So the electron actually even not a particle, and of course it cannot actually spin around itself. And people, when people was trying to build quantum, when they were building quantum theory, they also thought that maybe this spin corresponds to the rotation of the particle around itself, right? But then when you calculate the velocity at which the particle supposed to spin around itself, this rotation, this velocity of this rotation would be larger than the speed of light. So because the particle is so small, this rotation would be so fast. So it's not real rotation, but this is something that can be imagined. as a rotation. Okay, this the same way as the electron is not a particle, but it can be imagined as a particle, and this way we describe the particle, the electron as a particle, depends on the particular situations. Sometimes it works better, sometimes it works worse. The same for the spin. Spin can be imagined as a rotation of the electron or any other particle around its axis, and sometimes this classical analogy works better, sometimes it works worse, but the point is that spin exists in reality, and this is what the experiment tells us. And then the question says that I could be wrong, but I think I read something about spin being just a name and it doesn't actually spin. Yes, so it's it doesn't really spin. In fact, we even cannot say what it is because as we discussed, there is no particles, there is no waves, and the electron is something in between. We as people, we just used to think about something in terms of physical models, right? We describe like electromagnetic wave as a wave in space because we know these waves on the sea, on the water, but this is just a model, and in reality electromagnetic wave is not a wave, right? In reality, electromagnetic wave consists of particles known as photons, and those particles also behave as particles in some particular experiments or effects. For example, when photon is emitted by a quantum system, like any molecules, right? Any molecule can emit photon, emit light. And when it emits light, it's emitted by single particles, by single photons. But in other cases, these photons, they behave as waves. And the same way here. So it's the electron is not a particle. It's sometimes it behaves as a wave, sometimes it behaves as a particle, and when we describe spin, we just assume, because this is the way we it's a natural way to think about the things. Like, think about that electron is an electron, and hence, since this is a particle, it can rotate clockwise, counterclockwise. But in reality, electron is something else. We just don't know what it is, and we cannot imagine what it is, because all our experience or our models are taken from classical physics. So we cannot describe electron in using classical things, classical models, because this is not classical. Okay, so you can imagine spin as a intrinsic rotation, intrinsic angular momentum, but please be well, remember that this is not a real rotation. Okay, so the value of spin We will talk about, for now, we will talk about spin 1/2 only. And the experiment says that for example, particles like electrons, they have the value of spin equal h bar over 2. Okay, so this is simplest and the most important case of particle like electron with the spin equal h bar over 2. This is the value of this spin. Okay, and the experiment also tells us that there are only two orientations for this rotation possible. So only two orientations are possible. So what it means? It means that for a given axis, so I put this axis z here, right? For the given axis, and this axis is naturally given by the setup, like experimental setup, or by the direction of magnetic field, because spin feels or interacts with magnetic field. So this direction is defined somehow. And for the given direction, let's write this for a given direction. So for the given direction, only two orientations of the spin is possible. And what it means? It means that spin is represented by operator with only two eigenvectors, eigenstates. Okay, so we will use this fact in a minute. And yeah, also let's write this down, this line. So the usually this z, right, this direction of orientation of the z direction, it is a direction of the setup and given is the direction of a setup and given. It is given. So as an example, let's consider the very famous experiment. It's named after two scientists, Stern and Gerlach experiment. Stern and Gerlach. Germany's names. Gerlach experiment. Stern-Gerlach experiment. So what they did, they took a source of the particles, and the source emits particles with the spin 1/2. So the spin of each of these particles is h bar over 2. So these are particles with spin 1/2, and and of course they did this experiment even before they observed the spin, right? So the existence of the spin is actually the result of this experiment. So they took the source of particles and without any magnetic field, the particles hit the same spot on a screen, right? So like I take a screen, put on the way of these particles. So this is screen. Screen. So these particles created the bright spot on this on the screen. Okay, so nothing curious, nothing particularly interesting. What they did after that, they put the system in a magnetic field, right? So this for these particles, we turn on the magnetic field like this, in this direction. So this is B field, magnetic field. Okay, and what experiment tells us, the beam of these particles is split into two beams, two races with like this. So with the magnetic field, these particles, they created two bright spots on the screen. This is the second case with magnetic field. So magnetic field somehow broken the degeneracy, okay, and created two spots on the screen, okay, and we denote these these spots by +1/2 and -1/2. Okay, so when the theory of the spin has been established or built by Pauli and other scientists, after that we know that the result of this experiment is the existence of the spin and the fact that in this magnetic field, which is the direction of z direction, right, each particle in this array of particles gets polarized either along magnetic field or either parallel magnetic field or anti-parallel to the magnetic field. Okay, so this is the so the spin is the system with just two possible positions, either along magnetic field or anti-parallel to magnetic field. Okay, and that's why we get these two spots. So in magnetic field, these two orientations of the spin, they became distinguishable. Okay, what it means? It means that without magnetic field, each particle, each electron is in the superposition of both orientations of the spin, up and down. And this is superposition. But when we turn on the field, or when each electron gets to the magnetic field, this magnetic field acts as a measuring system. Okay, so it checks or measures in which quantum state this electron is in, either up or down. And then each single electron state collapses to either state up or state down. And when it collapses to the state up, the electron goes up. When it collapses to down, it goes down. So we got these two spots on the screen. Okay, so this spin is a quantum quantity before measurement, we get superposition of two spins. You can even actually write this somehow like this. So before measurement, we have the psi state with state up and state down. And the state up is denoted by C up, state up. Okay, and down is C down, state down. Okay, and after turning on the magnetic field, so in magnetic field, this state collapses either to state up or state down. This superposition collapses either to state up, state down, with the same probability, with probability 0.5, and this one also is with probability 0.5. Okay. And probabilities, of course, given by this coefficient. So C up modulus squared is equal to 0.5, and C down squared is also 0.5. Okay, so one single spin is a system with two states, either up or down, in a according to the particular direction in space, which is given by the direction of magnetic field. And this is exactly, I mean, this is the psi vector of a qubit, right? So it's a system with two possible quantum states, either up or down. So one single spin works as a qubit. And in fact, some modern designs of quantum computers, they use this fact. They use spins as a qubit. Some solid state versions of quantum computers. There are some pros and cons of working with spins, and we will discuss those later. Another point here about this Stern-Gerlach experiment is that after measuring the spin state, meaning after applying this magnetic field, let me actually copy this somehow. Copy. Paste. Okay, so when we measure this spin state by applying magnetic field, and we got the two spots, right? Plus 1/2, minus 1/2. Of course, we can apply magnetic field again, but to the one of the states, like this. So this is another magnetic field. And the result of this experiment is only one spot, only this spot. So it doesn't affect the spin state anymore. So when the degeneracy of the spin state is lifted, and we got only plus 1/2, applying magnetic field in the same direction doesn't create any other types of doesn't create other spots. So it means that when we measure the spin, when the psi function collapsed to the state 1/2, the electron stays in that state, yeah, so this additional magnetic field doesn't create any other spots. and at the same time, it also means that there are only two possible orientations of the spin. But when we oops, how they, okay, let me put it like this. So when we apply magnetic field in the another direction, like along x direction, like this, so this is magnetic field. This magnetic field creates again two orientations of the spin, and we create again two trajectories. It's hard to write this on a plane, but you can imagine, like when we apply magnetic field in the orthogonal direction, in the x direction, it again splits the beam into two different beams, two different states, plus and minus, but now in the x direction. Okay, so the fact that the electron is in the state 1/2 in the z direction, it can collapse to 1/2 and minus 1/2 in x direction. Okay, so it might be not easy to imagine. So let me actually redraw this picture. So we have these electrons here, right? So we can apply magnetic field in the z direction. So this is my z direction, this is x direction. Okay, I apply magnetic field in the z direction, and this magnetic field splits the electrons into two beams with 1/2 and minus 1/2. Minus 1/2 in z direction. Okay, and now if I apply magnetic field again in z direction, this magnetic field doesn't change the things, so it's still in 1/2 in the vertical. Let me change this 1/2 minus 1/2 to the orientation of the spin. So let's say this one oriented up in z direction, this one down in z direction. Okay, and again, if I apply another magnetic field here, it doesn't change the state of this spin. It's still in the vertical direction. But then, for example, for this upper beam, I apply magnetic field in the x direction, like this. So this is my magnetic field in x direction. Okay, and after that, the beam gets splitted twice, like this, but in the x plane, in the x direction, right, in the zy plane, with orientations of the spin in the x. So this is x direction, and this is like this, right, minus x direction. Okay, and then if I get these particles to the screen, they will again create other two spots here and here, and it will be left and right, not left and right, but up and down electrons, but in the x direction. Okay, so it's it needs some time to understand these things, how all this works. The key points here, I think, is that the spin is a state with two orientations, up and down. But since x, y, and z directions in space, in nature, they are equivalent, right? It doesn't really matter which direction we denote as z, as x and y. The same happens in all three orientations. Okay, so we have three different operators that describes all these things. Three orientations, three operators. Usually the orientation z, as I said, it is given by the type of the system, by the direction of the magnetic field. So somehow this z direction is pre-selected, even though x, y, and z, they are equivalent, like perfectly, totally equivalent. But yeah, so three different directions, three different operators that describe the state of the spin. Okay, these states, these orientations of the spin, they described by spin matrices, spin operators. They are named S operator X and is given by h bar over 2 sigma x. The second one is Sy, it's equal to h bar over 2 sigma y. And Sz is given by h bar over 2 sigma z, where sigma x is the first Pauli matrix 0, 1, 1, 0. Sigma y is the second Pauli matrix, is given by 0 minus I, and 0. So we already met these two matrices today, right? In the problems. And sigma z is the third Pauli matrix with components 1, 0, 0, minus 1. Okay, so all these three Pauli matrices Pauli matrices. And when I apply this when I multiply this Pauli matrices by h bar over 2, I get the spin operators. Spin operators. Spin operators. So these spin operators have eigenvalues h bar over 2 and minus h bar over 2. So it's very easy to see that from this sigma z matrix, because it's already a diagonal, right? So sigma z matrix, which is 1, 0, 0, minus 1, it's already diagonal matrix, which means 1 and minus 1 are the eigenvalues of this matrix. So the eigenvalues lambda 1, 2 is plus 1 and minus 1. These are eigenvalues of this Pauli matrix. And if you diagonalize the other two Pauli matrices, they also give the same eigenvalues, plus and minus 1. Plus and minus 1 eigenvalues, they simply correspond to two different orientations of the spin, either plus 1, which is up, or minus 1, which is down. Okay, and hence the the eigenvalues of the corresponding spin operator, which is h bar over 2 sigma z, right? It is equal to plus h bar over 2 and minus h bar over 2. So this is the value of possible spin, h bar over 2. And when it's equal to plus h bar over 2, the spin directs up. When it's minus h bar over 2, it directs down. According to the direction of magnetic field. Okay, so let us write this down like this. So all Pauli matrices have the same eigenvalues, values plus minus 1, okay? And that's because of two orientations in space. Because of two orientations in space. But eigenstates are different. But again, states are different. And since we will need these eigenstates of the spin, let us make a table with the following. So for the z component of the spin, we have up and down states, up and down states. Let's indicate for the z component of the spin, and it's given by the basis vectors 0 and 1. So the state up is given by the basis 1 0, which is 0 state that we already saw. This is another reason for using these 0 and 1 states in the when we describe a qubit. And the spin down is given by 0 1, which is state 1. Okay, so again, this is for the z component. These are the eigenstates of the sz operator or sigma z. They have the same eigenstates or eigenvectors. Okay, so this is for the z component of the spin. For the x component of the spin up and spin down, we have another very popular, very frequently very known pair of states. 1 over square root of 2, composition 0 plus 1. And minus is given by 1 over square root of 2, 0 minus 1. Okay, we already discussed these states just by as an example of superposition. Like when you have 0, when you introduce 0 state, you introduce state 1, you can take the superposition of 0 and 1, and this is we denote them by state plus, state minus. So in the when we're talking about spin, it's better to denote the spin by up and down. So the name, when it's up, it's composition 0 and 1. And when it's down, it's composition 0 minus state 1. Okay, and the final, for the y orientation of the spin, again, up, y, and down, y, it gets yet another pair of eigenvectors, almost like the one for the x, but with an important difference. So it's 0 plus I times 1. And likewise for the down, 0 minus I times 1. Okay, so this is for Sx or sigma x, and this one is for S y and or sigma y. Okay, so this is the this is the eigenvectors or eigenstates of all three Pauli matrices. Each Pauli matrix is a matrix 2 by 2, and it gets two different eigenstates or eigenvectors. The basis vectors that we will widely use for a qubit, 0 or 1, they are essentially the eigenstates of the Pauli matrix sigma z. Okay, and other two pairs of vectors for the x and y orientations of the spin, they give the, they are represented by the superposition of 0 and 1 of different kind. All right, so yeah, I know it might be kind of difficult to grasp this, but I believe you will get use of it. Okay, or yeah, maybe after some practicing. And let's describe a couple of problems now, and then conclude today's lecture. So for the problem one, so let's demonstrate that spin is not measurable in x and y direction at the same time. Let's demonstrate that spin is not measurable in x and y directions. Or, in other words, find the commutator. Find the commutator. Find the commutator. Right, so when we need to check if quantities measurable or can be measured in different simultaneously, we need to find the commutator of these two operators. So for the commutator for the x and y, Pauli matrices is sigma x, sigma y minus sigma y, sigma x, right? And for the sigma x, we have Pauli matrix 0, 1, 1, 0. So it's 0, 0, 1, 1, 0. And for the for the matrix y, it is 0 minus I, 0. 0 minus I, 0. And the same in reverse order. 0 minus I, 0, 0, 1, 1, 0. Okay, so the product of the first two is gonna give us another matrix row by column. 0, 0 is 0, 1 times I is I, so it's I, the first element. The second, 0 minus I, 0, 1 times 0 is 0, so it is 0. Next, 1 times 0, 0 times minus I is 0. And finally, minus I times 1, minus I, okay? And then minus second pair. It's gonna be it's gonna 0, 0, minus I1, so it's minus I here, then 0 here, then another 0 here, of course, and finally I times 1 is I, right? Okay, and so it's gonna be I 0, 0 minus I plus I 0, 0 minus I, right? Or it's equal to 2I 0, 0 minus 2I. Or if I take 2I from this matrix, so it's going to be 2I, 1, 0, 0 minus 1. And this last matrix coincides with the sigma z. So this is sigma z. Okay, so it's equal to 2I times sigma sigma z. Okay, yeah, so indeed the commutator of sigma x and sigma z are equal to 0, and in fact it's equal to 2I sigma z. Okay, and we can get the other three formulas, like for example for the sigma, sorry, here it's sigma y. Like sigma z, sigma x, it's equal to 2I sigma y, and etc. So in fact, the commutator are in 0, and the spin in x and y direction cannot be measured simultaneously. And likewise, for the z and x and z and y, all three orientations of the spin cannot be measured simultaneously in one experiment with high precision, with high accuracy. Okay. So let's discuss another problem. Sorry, y3, 2. Problem 2. So let's define or find the determinants and the traces of Pauli matrices. Yeah, so this word trace traces is a new word to you. It's nothing but just the sum of the diagonal elements in any matrix. So this is also a good way. It's a good time to introduce this operation traces. All right. So for the determinant of sigma x, so that's equal to what is sigma x? 0, 1, 1, 0, 0, 1, 1, 0. It is 0 times 0 minus 1, 1 times 1, which is minus 1, right? This likewise for determinant sigma y, it is 0 minus I 0, which is minus 1 again. And for the determinant sigma z, it's also minus 1, right? So it's also 1 times minus 1 minus 0, so it's minus 1. So the determinants of all of any Pauli matrix is minus 1. And what about traces? So the trace, we denote this like this trace of sigma x first is equal to trace of trace of 0, 1, 1, 0. So trace is the sum of the diagonal elements. So in this case, trace is equal to 0, just because this is just 0 plus 0. Trace of sigma y is also equal to 0, because it's 0 minus I 0, right? So it's also 0. And finally, trace of sigma z, which is 1, 0, 0 minus 1. Again, it is 0, because 1 minus 1 is 0. Okay, so the traces of any Pauli matrix is equal to 0. Okay, this is the answer.
Professor.
Yes.
So you only do the diagonal addition from left to right, only from top to the bottom, not from bottom to top as well. So like in the case of the last one, it's 1 plus -1. You don't also do 0 plus 0. You only do one
Yeah.
addition. Okay.
Yes. So trace, let me write this, maybe a general formula like this. So trace of any matrix is like trace A11, A12, etc., A21, A22, etc., and etc. So it's equal to A11 plus A22 plus A33 plus etc. So it's sum only the diagonal elements. This
Yeah,
is
from left to right, from top to bottom only.
yes, exactly.
Thank you.
All right, and the final problem number 3 for today. Problem number 3. So for the particle in state up y. Okay, so this is the spin polarized state in the direction y. Okay, what is the expectation value? What is the expectation value? value of measuring the spin, in the z direction, Okay. So we somewhat try to discuss it here in the Stern-Garlock experiment, but I mean up to the replacement x by y. So we have the particle polarized in z direction. Oh, sorry, in y direction. And then we decide to measure the state of the spin in the x direction. So you might guess what would be the expectation value, right? So let me draw this once again. So this is the z, this is x, this is y, okay? And I prepared my spin, the orientation of the spin along y direction. So this is state up y, along y. Okay, my particle is polarized along y. And then I do the measurement in this z direction, So what will be the expected value from the experiment? What would be the expectation value? In other words, it asks us what will be the projection of this y state on the plus or minus z. So I mean, of course, it will be projected to the up z or down z with the same probability, right? And when we average all these results of experiment, in result we will get 0, because positive z and negative z come with the same probability. So the average value will be 0. Okay, so let us prove this assumption. Okay, so for the up y state, we have this here. So it is here. It is 1 square root of 2, 0 plus 1 over square root of 2, 0 state plus I 1 state. Okay, so we have this state. It is prepared, and then we measure this, and then we measure the spin in z direction. It means that we need to find this expectation value in z direction. So for the first state, I mean for this up state, I mean this one, the up state y, then sigma z is the 1 0 0 minus 1. So it's 1 0 0 minus 1, and then again this up state like this. So expectation value, right? Expectation value. So let me continue here. So for the up state, I need to take the Hermitian conjugation of the ket to write the bra. It's gonna give me 1 over square root of 2. Next 0 state, right? Minus I 1 state. It's too bulky to write this like this. So let's rewrite this up state first in the matrix form. So let's rewrite this state, which is 1 over square root of to 0 plus I1 in the matrix form. So it is equal 1 over square root of 2. Then this 0 state is 1, 0, right? Then plus I and 0, 1. Okay, so it is equal to 1 over square root of 2, 1, I. Okay, so much ID. And this is cat, and hence for the bra of the same vector, I get 1 over square root of 2, the row 1 minus I. Okay. All right, and now I write this expectation value formula again. So for the bra, I get 1 over square root of 2, 1 minus I. Then the sigma z matrix 1, 0, 0 minus I. And finally for the cat, I get 1I. Okay. And 1 over square root of 2 taken twice, so I get 1 over 2. And I get 1 over 2, 1 minus I. And then the product of these two guys is 1 and minus I, right? So it's gonna be 1 minus I. So 1 times 1 is 1, minus I is minus 1, so the result is 0. Okay, so the expectation value is 0. So this should give you some like intuition about the quantities, expectation values, and the result of one particular experiment, right? So in one particular experiment, we can get either plus 1/2 or minus 1/2, depending on which state the initial state collapses into, like either state up or state down. But since these two realizations, they have the same probability of happening after taking like 100 or 1,000 or million experiments. They come with the same probability, so the all realizations cancel out each other, and the expectation value is 0. Okay, so that's why expectation value is 0. Yeah, so do you have any questions regarding this part? All right, so let me pause.